Good day, students. In this group, we're going to be going over how to make use of the basic differentiation rules, the constant rule, power rule, constant multiple, and sum and difference rules. Okay. All right. So before we get started, what I like to go over is just some notations and basically different notations that can be used to represent the derivative of a function. Okay. So just to familiarize you with the notation, because you're going to be seeing different ways of expressing the derivative in different textbooks and problems. So notation for derivative, just keep in mind the fact that the derivative of a function, ddx of a function, let's put this in black, ddx of a function f of x is the same thing as the function prime, see, ddx, same thing as a function prime, and is also the same thing as can also be written as big D x of the function. Okay, and all this basically they all mean the derivative of the function f of x. So if you want to see it in word form, you can just say the derivative of a function f of x. Okay, so these are the different notations for writing the derivative. And for computational convenience, the primes sometimes will suffice. And in other cases, when you're solving certain kinds of differential equations where you want to do separation of variables and things of that nature, this notation could be much more powerful or useful. Okay, so different formulations or representations are appropriate for different kinds of problems. All right, so let's go ahead and take a look at the first rule we're going to be looking at. Rule number 1 is the constant function rule. Constant function. Okay, we know what a constant function is. A constant function is a function that doesn't change. It has exactly the same value for all input values of x. Okay, so what is a constant function rule? It just basically means says that the derivative dx of a constant function, let's say c, is equal to 0. Okay, so that's a constant function. All right, so before I basically go over examples using this formula, this rule, the constant function rule, let me just show you a formula sheet I have generated, differentiation rules, that you can download and make use of. And then I also have an empty sheet that you can practice your formulas with. So this document can be found on math.serve.com under the calculus section. You just download it and then you can make use of all these cool formulas. Okay, so basically today we're going over formulas 1, 2, 3, and 4: constant, constant multiple, power, and sum and difference rules. Okay, as you progress in your skills of differentiation, then you can make use of much more elaborate formulas. Alright, so don't forget you can get this document at microserve.com. So let's go back to the example. Alright, so derivative using the constant function. Now let's look at some examples. Alright, so let's title it examples. Okay, number 1. The task is find u prime if u is equal to the natural logarithm of 2. Okay, alright, so how do we do this? What is u prime? Remember that u prime is just another way of writing du dx. Okay, du dx. Alright, so basically what we're looking for here is the derivative ddx of the natural logarithm of 2. Alright, so natural logarithm of a constant is going to be a constant, right? So don't get confused here. This is a constant. So we're going to use a constant multiple rule since the argument of a derivative is a constant. So the answer is simply going to be 0. Okay? All right. Let's try another example. Number 2. The task is to find the derivative with respect to x of y, where y equals e to the third. Okay. All right. So remember, d with respect to x of y is the same thing as the derivative of y, and d dx of y is the same thing as dy dx. Okay. All right. So we're gonna basically look for, since y is e to the third, we're looking for d, the derivative with respect to x of e to the third. Okay. So what is this? E to the third is a constant, right? Is a constant. So since this is a constant, we're just going to use the constant multiple rule here, and your final answer is going to be 0. All right. So all these constants, they come in different forms. So you have to be able to identify them and distinguish them uh, from functions that are not constants. Okay. All right. Number 3, find d dx of pi to the third power. Okay. All right. So we're looking for d dx of pi to the third. Now, is this a power function or constant function? Well, this is a constant raised to a constant, so it is a constant function. It's not a power function. So we can still use the constant constant function rule here to evaluate this derivative. So our answer is going to be 0. All right. So there you have it. Okay, let's shift to our second set of rules. Rule number 2 is going to be the power rule. Okay, the power rule. All right, so for the power rule, this is the formula for the power rule right here. The derivative of a power, x to the n, is given by n times x to the n minus 1. All right, so basically what this formula is telling you to do is when you're taking the derivative of a power of the form x to the n, you bring down the power to the front and multiply it as a coefficient of x, and then you subtract 1 from the power and insert it as the new power. Okay, so that's basically what the power rule is telling you to do. All right, let's take a look at some examples. All right, examples. So the task is as follows. Let's call this A, so don't get confused. Find y prime if y is equal to x to the 5th power. Okay? All right. So we're going to be using the power rule here clearly because we can see that this is the power of the form x to the n. So y prime in this case is going to be what? In this problem, n is 5, right? So if you want to look for y prime is x to the 5th prime. So the rule says you bring the power to the front as a coefficient, so bring the 5 down 5 times x to the, and then subtract 1 from the existing power, 5 minus 1. Okay, so power down and then subtract 1 from the power. So let's simplify that, and that will be the expression for our derivative. Okay, so it's going to be 5x to the 4th. That is what y prime is. Okay, so there goes your final answer. All right, let's try another example. Example B. For this one, we're going to find dy dx if y is equal to x to the 7th power. All right, so let's work this one out. Dy dx is basically equal to, since y is x to the 7th, d dx of x to the 7th. We can clearly see that this is a power, so we're going to be using the power rule here. Okay, so what you're going to do, you power down, bring down the power, 7 times x to the, and then you subtract 1 from the power, 7 minus 1. Okay, so that's the derivative. So it's going to be 7x to the 6th power as a derivative of x to the 7th. All right, now the C part. In this case, all right, so for question number C, we're going to find y prime if y is equal to 1 over the square root of x. Okay, all right, So let's do this. Now, if you take a look at this problem, this does not look like a power function. The question is, can we rewrite this as a power so we can basically make use of the power function we already know how to use so we can find the derivative? So if you think back to the properties of exponents, I can express the square root of x as a fractional power, x to the 1/2, same thing as the square root of x, and that equals, and then using the reciprocal property of exponents, I can express this as x to the negative 1/2. Okay, and you see what we have now? We have a power. Okay, and now we can use the power, albeit a negative fractional power, we can still use the power rule to evaluate this derivative right here. Okay, so y prime is going to be x to the negative 1/2 prime. Okay, so the same power rule applies here. So to do that, what we'll do is the power down, bring down the power is negative 1/2, negative 1/2, x to the, and then you subtract 1 from the power, negative 1/2 minus 1. Okay, or you can write 1 as 2 over 2, and then this becomes negative 1/2 times x to the, and then if you subtract 1 from negative 1/2, you have negative 3 over 2. Okay, and if we want to rewrite this, we can rewrite this as negative 1 over 2 times the square root of x to the third. Okay, so this would be the simplified form. 1 over 2 times the square root of x to the third. All right, let's try another example. Let's see how about, for example, these two using the power rule. Find d dx of f of x equals 1 over x to the 4th. Okay, this is a rational function, so one term. Now the question is, can I express this as a power function so I can use the formula we already know? And the answer is absolutely yes, right? We can use the reciprocal property that we just talked about earlier. We can express this as x to the negative 4, like that. That simply tells us that d dx of the function is going to be the derivative of this power function we already have here, x to the negative 4. Okay? So what's the derivative of x to the negative 4? You basically power down the exponent. It becomes negative 4, and then you subtract 1 from the exponent. Negative 4 minus 1 is negative 5, and this can be expressed as negative 4 over x to the 5th. Okay? Alright, so that's that for power function. Now let's shift our attention to another rule. It's pretty easy. This one is known as the constant multiple rule. Constant multiple rule. Okay, all right, so what does the constant multiple rule tell us? Well, just basically, let me write down the formula first, and then we'll talk about what it's telling us. If you have derivative of a constant be multiplied by a function, this is the same thing as a constant multiplied by the derivative of the function. Okay, you know derivative basically means instantaneous rate of change, right? So if a constant isn't changing, the derivative has no impact on that constant, so you can factor it out and shift the attention of the derivative on the function that's changing. But if you had only a function, then that would be 0 because it doesn't change, right? But if you have a constant multiplied by a function, what this formula tells us, or this rule tells us to do, is you just factor out the function, the constant, and then differentiate the function. Okay? All right, let's try out some examples here. Okay, the A part of example 3, part A. How about finding d dx of 3x squared? Uh-oh, this looks a little bit different from what we've been doing. This, we have a power function being multiplied by a constant. So based on the constant multiple rule, in order to do this, what we have to do is basically focus our attention on differentiating this function right here. This 3 is a constant, so what do we do with it? We factor it out, factor out the 3, put it in front of the derivative, and then you differentiate the function x squared. Okay, now we can apply the power rule to this piece right here. If we do that, it's going to become 3 times, remember what the power rule is, right? For the power rule, you just power down the exponent and then subtract 1 from the exponent and put it as a new exponent. So if we power down the exponent, it's going to be 2x to the, and then subtract 1 from the exponent. 2 minus 1 is 1. Alright? So if you simplify this, you get 6x as your derivative. Okay? So there you have it. Alright, let's try another example. Let's have you find y prime if y equals 3e to the pi. Okay? Alright, so let's go ahead and do this. So y prime is basically 3e to the pi prime. Okay? Alright, so first thing we want to do is we want to factor out the constant. So what's the constant here? Wait a minute, the whole thing is a constant, right? So there's nothing to factor out. So guess what rule we're going to use here? We're going to use a constant rule, the constant function rule that we studied first. What did we say the derivative of a constant was? The derivative of a constant is 0. So since this entire thing is a constant, don't let it deceive you. The derivative is simply 0. Alright? So there you have it. Okay, that was a trick question though. Anyway, part C, find the second derivative y double prime if y equals 2x to the 4th. Now the second derivative y double prime just basically means when you find the first derivative, you apply the differentiation process again to your results to get the second derivative. Okay, this is really important in analysis of function and also in physics when you're computing things like the velocities and acceleration and things of that nature. Alright, so how do you find the second derivative? This is y double prime. Let me write it properly so you don't get confused. Y double prime is you're differentiating twice. Okay? Alright, so just for notational reasons, y double prime can also be written as d squared of y dx squared. Okay? The same thing as y double prime. It means the second derivative. Okay? Alright, so we're looking for y double prime. So what we're going to do it step by step, okay? Let me just show you something. So y double prime is basically d dx of dy dx. Right? So when you multiply it out, that's why you get d squared y dx squared. Anyway, that's just a side note. So what we're going to do, we'll do it step by step. We'll do the first derivative using the appropriate rule, and then we'll do the second derivative on the result we got from the first derivative, okay? So y prime is 2x to the, I'm getting ahead of myself. Y prime is 2x to the 4th prime. 2x to the 4th prime. Okay, so what rule are we going to use here? How about the constant multiple rule? Because we have a function and a constant, so we can extract the 2 from the differentiation process. So it's going to be 2 times x to the 4th prime. Okay? Alright, so we're going to apply the power rule here to x to the 4th, and that's going to yield, you know what the power rule is, right? You power down the exponent 4 times, and then you subtract 1 from the power. 4 minus 1 is 3. Okay? Alright, so y prime, the first derivative, is going to be 8x to the 3rd. Okay? Are we done? Absolutely not. We were asked to find the second derivative, right? We just found the first one. So to find the second derivative, all you're doing is you're taking the derivative of the first derivative, right? So at 8x to the 3rd is the first derivative, so we're going to take the derivative of that, or 8x to the 3rd prime. Alright? Okay, so how do we do this? We have a constant and a function, so we can use the constant multiple rule here again. So we have 8 times x to the 3rd prime. Okay? And now let's differentiate this. What rule do we use here? This is a power function, right? So we can use the power rule here. So it's going to be 8. Then the power rule, you just power down the exponent, 3 times, and then you subtract 1 from the power. 3 minus 1 is 2. Okay? All right, and then when you multiply everything, you get what the second derivative is, which is 24x to the second power. All right? So there goes an example of higher order derivatives. That's another way it's called the multiple derivatives. Higher order derivatives, applying the constant multiple rule, the power rule, and also the constant function rule. Actually, we didn't use the constant function. We just use the power rule and then the constant multiple rule. Okay? All right. Now that takes us to the last one we're going to be working on today, which is the sum and difference rule. This is section 4, sum and difference rule. Okay. Remember, you can find all these formulas on math.serve.com. Download it, and then you can memorize them. If you have them all committed to memory, it's easier to recall them and solve problems quickly. All right, so sum and difference rule is as follows. So it says d dx of the sum of two functions u, the sum or the difference, u plus or minus v. This means the sum or the difference. Okay, two equations compiled into one is equal to the derivative of the first plus or minus the derivative of the second. Okay, so what does this look like? What does this look like? This looks like distribution, right? So it looks as though you can distribute the derivative into the sum or difference of functions, okay? So that's basically what it is. When you have a sum or difference of multiple terms, you can carry out term-by-term differentiation over the sum or difference of the multiple terms. Note, this does not apply to product or quotient of functions, okay? So note, this is a big note here because some people might have a tendency to create their own rules. So dx, the derivative of a quotient u over v, is not the derivative of the numerator divided by the derivative of the denominator. Don't do that, that's wrong, okay? And also, if you have the product, if you're taking the derivative of the product of two functions, it is not the derivative of the first function multiplied by the derivative of the second function. The whole idea of distributing the derivative to the terms within the argument applies only to the sum and difference of multiple terms, okay? Don't distribute derivatives to quotient or products. That's wrong. Okay, so keep that in mind. All right, now let's go ahead and try out some examples. A part, how about we find f prime of x, where f of x is equal to 3x squared minus 5x to the third plus pi. Okay? All right. So we take a look at this problem. We notice that we have a constant and a power. We have a constant with something in the denominator here. That doesn't look like a power. That looks like a rational function. And then we have a constant here. So the question is, can I rewrite this as just powers and constants? So it makes my life easy to carry out the derivative using the tools we already have. Yeah, we can do that. So leave 3x squared alone. And then this one I can rewrite using the reciprocal properties of exponent as 5. If you reciprocate a term, it negates the exponent. So it becomes x to the negative 3 plus pi. So this is excellent. I don't have any rational functions or any denominators with a variable to deal with here. They're all powers, so I can apply my power and constant multiple rule. Okay, so f prime of x. Now what we're going to do is we're going to do 3x squared minus 5x to the negative 3 plus pi prime. So how do you take the prime of the sum and difference of multiple terms? You do term-by-term differentiation. Okay, distribute the derivative to each term since we're only adding and subtracting. So it's going to be 3x squared prime, okay, minus 5x to the negative 3 prime plus pi prime. Differentiate every single term. All right, so that's how you do it. Okay, now let's look at each term and see what we can use to evaluate each one. So the first one, it looks like we have to use a constant multiple rule here. We have to factor out the 3 since the derivative doesn't impact it. So factor out the 3 and focus on differentiating x squared minus prime minus. Take out this 5, also constant multiple rule for this term here. X to the negative 3 is what we're going to be applying the power rule to. And how do we deal with this? This is a constant, so we're going to use a constant function rule to differentiate this, and it's going to be 0. Okay? Alright, so let's shift our attention to these two. So we're going to have, this is going to become 3 times, now using the power rule, here you power down, and then you subtract 1 from the power 1. Minus 5 times, you power down negative 3, you have to keep the sign. And then x to the negative 3 minus 1 is negative 4. Okay? Alright, let's simplify this further. We're going to have 6x minus times minus, actually this is plus 5x to the negative 4. And then your final results, actually 5 times 3 is 15. Sorry about that. Okay, and then your final answer is going to be 6x plus, using the reciprocal property of exponents, I can reciprocate this and negate the exponent, so it becomes 15 over x to the 4th. And there goes your derivative. Okay, so that's what f prime of x is. F prime of x equals 6x plus 15 over x to the 4th. And there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here. And please post the comments to let me know what you think about this clip. More clips can be found on mathgoodserve.com. There also you can find access to the differentiation formula sheet I just showed you. Thanks again for watching and have a wonderful day.